All right, welcome everyone. Let's get started. So first, just a few reminders. We have our 5th recitation exam this week. So either today's recitation or if you're in Thursday's recitation, you have it on Thursday. So just a reminder, we have our 5th exam this week. Also, homework due this week. We have homework on sections 03 and 04, so intervals of increase, decrease, and intervals of concave up, concave down. So those are due tonight. Don't believe there's any homework due Thursday. I should have checked that. But for tonight, we have homework on sections 03 and 04, increase, decrease, and concave up, concave down. For today, we're going to kind of keep talking about our optimization theme here and kind of get to the point where we look at applied optimization problems. All right, so let's kind of pick up where we left off last time. And we left off with example 6 here. So we were going to find the local max and the local min values of this function x times e to the x. And what we had just finished talking about, let me back up just a second, is when we have only one critical number on an interval, if that critical number is a local max or a local min, then it's automatically an absolute min or an absolute max on that interval. So if we only have one critical number, then we can actually say a little bit more about it than just a local max or local min. So let's keep that in mind as we go to these last two examples here. And if you have any questions as we're going through, feel free to just put it in the chat, and I'll either answer in the lecture or make a post on our website answering the question. So just let me know if you have any questions as we go through. All right, so our function here is x times e to the x. So the first step for finding these local maxes and local mins is to identify where the critical numbers are. And the way we do this is with our first derivative. So that's what we're going to do. Step 1 for finding the critical numbers is to calculate f prime. Now here, our function is a product, x times e to the x. It's a product of two x terms. We don't write it, but it's x times e to the x. So when we do our derivative, we have to use product rule. So let's implement the product rule. X times e to the x plus x times e to the x. Write down two copies of our product. In the first copy, we differentiate the first term. In the second copy, we differentiate the second term. So that's our product rule. Then keep differentiating. Derivative of x is 1, so that first term just becomes e to the x. And then the second term, derivative of e to the x is just e to the x. So our second term there is plus x times e to the x. And we're going to be working with this derivative, so it's going to be helpful to factor this. And so each of our terms there has an e to the x, so we can actually factor out 1 e to the x. So we're left with then 1 plus x as our kind of remainder term there. So we've factored our derivative. Now we're going to work with it. So this is the second part of finding the critical numbers, is we want to look for where the derivative is 0, and we want to look for where the derivative is undefined. So we're always keeping those two places in mind, where the derivative is 0 and where it's undefined. Now our derivative here is e to the x times 1 plus x. There's no division by 0, there's no square roots, there's no log functions. So our derivative here is always defined. So there's no contribution from that. But what about where f prime is equal to 0? Well, we take our derivative and we set it equal to 0, and we already have it factored. So that's one of our usual tricks or techniques on how to solve an equation, is to see if you can factor it. And once it's factored, you can set each of those individual factors equal to 0. And so if we look at this, the e to the x factor here, well, e to the x is never 0. So that's the one nice thing about exponential functions, is they're never equal to 0. The other factor is 1 plus x. So there we could set that equal to 0, and that's not too bad to solve. We get x is equal to -1. So we found our critical number. Well, we found only one, actually. So our critical number is x equal to -1, and we just want to check, is that actually in the domain of our original function? Yeah, it is. We could plug -1 into that original function, and there's no division by 0, there's no logs, there's no square roots. So x equal to -1 is in the domain of our original function f. No issues there. All right, so that's our critical number. So once we find our critical number, we need to classify it. We need to test it, figure out if it's a max, a min, or neither. And to do this, we have some options. We have the first derivative test, or we have the second derivative test. And whichever test you use, it's up to you. You can choose whichever test you want to do. So let's use the second derivative test here. So that means, as the name suggests, we have to calculate our second derivative. So let's calculate our second derivative. And we're going to do the derivative of our first derivative, and we're going to use the factored version here, this e to the x times 1 plus x. So let's differentiate that. So that is also a product. So let's write down 2 copies of that product. Put a plus sign in the middle. First copy, we differentiate the first term. Second copy, we differentiate the second term. We're just going through product rule again. So derivative of e to the x is just e to the x. Then we have our 1 plus x. And then the derivative of 1 plus x is just 1, so we won't write that. So our second derivative is e to the x times 1 plus x plus e to the x. And it might be helpful to try to simplify this. And we can do kind of the similar thing. We can factor an e to the x out. So if we factor out this e to the x, we're left with a 2 plus x. So 1 plus x plus 1 simplifies to 2 plus x. So that's our second derivative. All right, so now to do the second derivative test, we have to evaluate. So we take our critical number and we plug it into the second derivative. So we're going to take -1 and plug it into our second derivative. And when we do that, actually I'll do it down here. We get e to the -1 times 2 minus 1, which simplifies to just e to the -1. So we're just plugging in our critical number into our second derivative. And to help remember what the second derivative test says, we're just looking at the shape of our function when we're calculating f double prime. So e to the -1 is positive. Any exponential value is positive. So when our second derivative is positive, that means we have a concave up shape. And to help remember what the test actually says, let's draw in what the concave up shape looks like. It looks something like that. So what the second derivative test says is not only does it look like we have a local min, we actually do have a local min at this critical number. So we have a local min at x equals -1. Now, we can say a little bit more about this because there's only one critical number. So not only is it the local min, but because there's only one critical number, we can say that it's actually the absolute min. And since that's the only critical number, if we were looking for a local max, there's none. There's no local max here. So it can only happen at a critical number. There's only one critical number, and it's a min, so we can't have a local max. And then to actually figure out the absolute min value of our function, what's the value of our function? Well, we plug it into the original function. So we go back to our original function to figure out the value. And so if we plug -1 into that, we get negative e to the -1. And that's our lowest value of this function. All right. So just a little bit more practice finding critical numbers and classifying them using the first or the second derivative test. Let's try one more. Let's look at the function natural log 1 minus x squared. And we want to find the local max and the local min values of this function. So the same process. Find the critical numbers, and then we're going to classify them as a min, max, or neither. All right, so first step, we got to find the critical numbers, and that's going to involve our derivative. So let's calculate our derivative. So we have a composite function, so we have to use chain rule. So the derivative of the outer function, derivative of natural log, gives us the 1 over 1 minus x squared. And then we multiply by the derivative of our inner function, and that's chain rule. Keep going with the derivative. Let's differentiate that inner function. And when we do that, derivative of the inner function is -2x. And to make things easier, we'll put that into the numerator here. So we'll write this as just one fraction. -2x over 1 minus x squared. So we've just consolidated that into one fraction. And that'll make figuring out the critical numbers just a little bit easier because we want to look for where our derivative is 0 and then where our derivative is undefined. And when we have a fraction, the only way a fraction can be 0 is if the numerator is 0. And the only way a fraction can be undefined is when the denominator is 0. So writing it as a single fraction helps remind us what we're looking for here. Numerator to 0 and denominator to 0. All right, so what happens when we set the numerator equal to 0? That gives us -2x equal to 0, which gives us x equal to 0. Then we set the denominator equal to 0, 1 minus x squared. And if we solve for x, that gives us x equal to plus or minus 1. Gives us two possible values there. So it looks like we might have three critical numbers, but it's important to go back and just consider what the domain of your original function is. And so here, the domain of this function, natural log 1 minus x squared, natural log is undefined when the inner term becomes 0 or when the inner term is negative. And so here, our inner function becomes 0 at the endpoints 1 and -1, and then it becomes negative for anything larger than 1 or -1. So we end up with our domain being everything in between -1 and +1. And you could just kind of quickly check this. So just plug in a couple different x values just to convince yourself that this is the domain. Maybe like x equals 1. If If you plug that into the function, you'd get natural log 0, which is undefined. Maybe -1. You could try -1. You'd get natural log 0, which is undefined. Try something a little bit bigger. So maybe something like -2. Plug -2 in. And if we do that, we'd get natural log of -3, which is undefined. So anything outside that open interval from -1 to +1 is outside of the domain of our original function. We can't plug 0 into natural log, and we can't plug negatives into our natural log function, or inside a log function like that. So when we go through and think about our critical number, the critical number has to be in the domain of our function, and actually only one of these x values is in the domain of our function. It's x equal to 0. So we can plug that in, and we don't run into an issue. Get natural log 1. Natural log 1 is perfectly okay. So that's our only critical number here. And so we want to test it. We want to go through and classify. Is it a max or a min, or is it neither? And so, like we said, you could do either the first derivative test or the second derivative test. So we did the second derivative test. Let's do the first derivative test this time. And how this one works, this is where you do your sign chart for f prime, just like you're doing the intervals of increase, decrease. So let's write down our interval. We're going to set up our sign chart. Our domain is everything in between -1 and +1, excluding the endpoints. And then we found only one critical number, so let's plot that. It's 0 right there in the middle. And this gives us two intervals to consider. And we want to figure out the sign of f prime on each of those intervals. So if we look at f prime, we have it, we have a nice kind of already factored version here. So let's just write down the factors here for our sign chart. So -2x and 1 minus x squared. And then we'll see what that says about f prime, and then ultimately f. So -2, the first factor, is always negative. So it doesn't matter what interval we're on, that's always negative. To help us figure out the other terms, maybe we use a test number. So something like -1/2 for this first interval. So if we plug -1/2 into the x term, we get negative. And then if we plug -1/2 into that other term, we get positive. 1 minus x squared term, we get positive. So when we have a negative times a positive, we end up with positive. So f prime is positive on that first interval, which means f is increasing. And yeah, can't draw good there. I'll just write increasing. So we're increasing on that first interval. All right, let's go to the next interval. We'll figure out what f prime is doing there. So -2 is always negative. To help, let's plug in, use a test number. So maybe we could use something like t equal to +1/2. We're just going to test it. So we plug it into each of our factors. When we plug it into the x factor, we get positive. And when we plug it into the 1 minus x squared factor, we get positive. And so when we have a negative times a positive, the result is negative. And so that must mean f is decreasing on that interval. So what's happening is the interval to the left, we're increasing, and then on the right, we start decreasing. So we have the general behavior here is that we're going up on the left side, and then we switch, our graph flattens out, and we start decreasing on the other side. And so what the first derivative test says is we have a local max. At x equals 0. And that's because f prime switched from positive to negative. So that means we have a max. And to just help remember what the test says, it helps to just draw in the general trend. It's going up, then it goes down, we have a peak. So we have a max. All right, so we found our local max is at x equals 0, but there's only one critical number, so we can actually say a little bit more. Not only is it the local max, it's the absolute max. So the highest our function ever gets is at x equals 0. And since we only found one critical number and we know it's a max, there's no way we can have a local min. All right, so what is the absolute max value of our function? Well, we take 0 and we plug it into the original function, f of x. So our max value then is f of 0, which ends up being just 0. Natural log 1, which is 0. So that's the largest our function ever gets. All right, so when we're classifying a critical number, we have some choice. First derivative test or second derivative test. So whichever one you use, it's entirely up to you. Second derivative test, though, ends up being a little bit quicker. And that's what we're going to use in our primarily in our next section. So in Learning Outcome 06, we're going to see some examples for how to set up and use derivatives to solve applied optimization problems. And to get us going, we're going to start with example 1. And the examples, the applied optimization problems that we're going to be looking at are what are known as constrained optimization. So we'll see what that means in the course of this example. So let's start it. We want to find the maximum value of the function q equal to x times y if x plus y is equal to 2. So we have two equations there. And so for these problems, the first step in how to figure out where function q has a maximum or minimum is to determine which equation is the objective and which one is the constraint. So the objective equation, that's the thing we want to maximize or minimize. So here we want to maximize function q. We want to find the maximum value of that expression, that function. So let's write that down. We want to maximize q equal to x times y. We want to find the largest value of that function. Now the issue there is there's two variables. There's x and there's y. In all the problems we've looked at in the last section and the sections before, we've only been dealing with one variable. So the issue here is how do we find the maximum value for a two-variable function? And we're going to use that second equation to kind of simplify this down to a one-variable expression. So that other equation, x plus y equal to 2, that's going to be called our constraint equation. And why do we call it the constraint equation? Well, it puts some restriction on what our variables can be. So if we look at this equation, x plus y is equal to 2, x and y can't be anything. There's some restriction on what x and y can be. They have to add up to 2. So they can't just be anything. When we do their sum has to be 2. So the constraint equation puts some restriction on what your variables can be. So in this case, our variables are x and y. So the objective equation, that's the thing you want to find the maximum or the minimum of. And the constraint equation, that sort of puts some restriction or puts some limitations on the actual problem. All right, so once we've identified those two equations, we want to go through and kind of eliminate one of the variables. So we're going to work with our constraint equation in step 2 there, and we're going to solve for one of our variables, whichever one is easier. So in this problem, they're both equally easy. So let's solve for y. And if we do that, we get y is equal to 2 minus x. So then in step 3, we're going to take that expression, y equal to 2 minus x, and we're going to plug it into our objective equation. And this is going to give us a one variable function that we can then go on to optimize using all of our optimization techniques that we were just looking at. So let's start with our constraint equation, x times y. We're going to plug in our constraint that we solved, that we modified a little bit. So y equal to 2 minus x, we're going to plug that in. And when we do that, we get x. And instead of y, we're going to write the 2 minus x. And if we just multiply that out, we end up with 2x minus x squared. So the upshot here is we end up, once we go through these 3 steps, we end up with a one variable function, and we know how to optimize a one variable function. Critical numbers, test the critical numbers, you're done. All right, so let's see that in the next step. So we're going to optimize in step 4. We're going to go through and optimize that resulting function. So what was it? It was q equal to 2x minus x squared. So what is our process? Just did a few examples like this. So step 1, we want the derivative. Step 2, we want to figure out where the derivative is equal to 0 and where the derivative is undefined. Standard critical number type work. So first, let's get our derivative. So derivative of 2x is 2. Derivative of x squared is 2x, and we're subtracting. So we end up with 2 minus 2x as our derivative. Then we set our derivative equal to 0. And we solve that for x, and we get x equal to 1. Now our derivative here, we just want to pay attention. Is there any division by 0? Is there any logs, any square roots where we might run into trouble? No, it's just 2 minus 2x. There's no issues there. So there's no place where our derivative is undefined. So it looks like x equal to 1 is the only critical number. And we just want to mentally check that it's actually in the domain of our original function. So is it in the domain of q? So if we look at our function q, 2x minus x squared, there's no issue if we plug in x equals 1. So it's in the domain. All right, so we found our critical number. Now we want to classify it. And to classify it, we have a choice: first derivative test or second derivative test. So you can do either one. First derivative test will always give you an answer. Second derivative test can sometimes be inconclusive, but it's usually a little bit quicker. So we're going to do our second derivative test and see what we get. So we calculate our second derivative. And our first derivative was 2 minus 2x. So the derivative of that then is just negative 2. Then we take our critical number and we plug it into that second derivative. So we take 1 and plug it into the second derivative. Now here, there's really no evaluation work that we have to do. We're just plugging 1 into our second derivative. So we end up with negative 2 still. It's just a constant function. So you plug 1 in, you still get negative 2. What does the second derivative test say? Well, when the second derivative is negative, it means we have a concave down shape. Draw in what the concave down shape looks like, something like that. And what the second derivative test then tells us is we have a local max. At x equals 1 at our critical number. Well, we can actually say a little bit more. So we found only one critical number. So not only is it the local max, it's the absolute max. So we have an absolute max at x equals 1. All right, so we've just about answered the question. The last step is really just to make sure we've gone through and we've found everything the question is asking for. So we found where the absolute max occurs, but the question is actually asking for the maximum value of Q. So that's what we really want to find here to actually answer the question, is we want the max value of Q. So we take our function Q and we're going to plug in our critical number, and our function Q with the constraint equation was 2x minus x squared, so we're going to plug 1 into that. So we get 2 times 1 minus 1 squared, which ends up being 1. So that's the max value of our function. So that actually answers the question. All right. So that example is really just a kind of to illustrate what we're going to be doing with constrained optimization problems. So these are problems where we have two equations usually. One of them is our objective, what we're trying to maximize or minimize, and then the other is put some restriction, some constraint on what x and y can be. All right, so let's look at example 2. So here, let's read through it. And when we read through it, we're going to notice we don't actually have any equations here. So there's going to be more work, and the more work here is going to be really centered around just developing the mathematical model for this problem. And then once we have the model, then we'll go through and do all the calculus. All right, so let's read through this. We want to plant a rectangular garden along one side of a house, and we want to put a fence on the other 3 sides. And what we want to do is we want to figure out the dimensions of the largest garden that can be enclosed using 40 feet of fencing. So we're not given, in this example, we're not given the 2 equations, so we actually have to construct those first. We have to construct the mathematical model. So there's really going to be a step 0 here where we do that. And to help with that process, we're going to draw a diagram, we're going to introduce variables, and then just interpret what's going on in this problem. All right, so let's start with a diagram. And we see this word rectangular. So we're going to be planting a rectangular garden. So let's draw in a rectangle. And one side of that rectangle, one side of our garden is going to be planted along a house. So here's our house. And kind of we've drawn our rectangle. We've put it alongside a house. Let's introduce some variables. So we know for a rectangle, there's really two distinct dimensions. There's the width, and then there's the depth of our rectangle. So we'll just call those X and Y. If you want to use like L and W, fine. So you just want to introduce variables. And for a rectangle, opposite sides of a rectangle have the same length. So this side must have length Y, and this side must have length X. All right, so what are some kind of usual calculations that we might do with a rectangle? Well, area is X times Y, length times width. We might do perimeter. It's another common one. And that's where you go along all the edges of your rectangle and you just add up the lengths. So if we go around our rectangle, this side has length Y. So we'd have Y. Then the next side has length X. So we add in X. Then the other side has length Y. So we add in Y. And then the perimeter of this entire rectangle, we finish off the fourth side, which also has length X. And the perimeter would be 2X plus 2Y. Now for this actual problem, we're not actually putting any fence along one of those sides. So we're not going to be dealing exactly with the perimeter. It's going to be a little bit different. So we're not putting the portion of our garden that's along the house does not need a fence. So when we go along the edges, the side along the house here, we're not going to put a fence by. So if we wanted to figure out how much fencing we would need, it's going to be similar to a perimeter calculation, but we're just going to be excluding one of the sides. So we would need that first side on the left. So we would need a fence for that. So that would have length Y. Then we would need fencing for the side opposite the house. So plus X. Then we need fencing for the right side, plus Y. But then when we get back to the house there, we don't need fencing along that side. So we don't include that. And so for the actual amount of fencing that we would need, if we simplify this, it would be X plus 2Y. So right now we're just going through and we're kind of just developing a mathematical model for this problem. We drew our diagram, we introduced variables, and now we're going through and thinking about what are some of the calculations, what are some of the formulas we might need for this kind of object that we're developing. So area, X times Y, and perimeter possibly, or in this case, more likely the amount of fencing. All right, so as just a kind of a little aside here, what are some possible examples of different sized gardens? You know, this isn't required, but it helps to just kind of conceptualize what's going on. So you might have like a really thin garden here, where like those little thin sides are 4 feet long, and then the width there is 32 feet. So we could have a really thin garden that stretches, you know, almost the whole side of a house. And in this case, our area would be 128 square feet. We might have something maybe like 15, 15, and 10. So those three sides of fencing would add up to 40. And in this case, the area would be 150 square feet, so a little bit larger. And then possibly we might have something, a rectangle 12, 16, and 12, where the area would be 192 square feet. So it seems conceivable that there is some kind of optimal configuration that would give us the largest sized garden. And that's what we're going to figure out in the rest of this problem. We'll go through the actual calculation and figure out what's the value for x, what's the value for y. So there's a question. When we did the amount of fencing here, you just want to make sure. So when I did the amount of fencing, I didn't include this x value from our perimeter. And so when you're kind of developing these equations, you just want to make sure that it's consistent with your diagram. So this was the side that I took away from, and that's had length x. So that's why I removed an x. If I had labeled things differently, then maybe I would have taken away some other variable. So as long as you're consistent with your variables, you can use whatever you want. So maybe, I might have had the house set up, maybe if I drew this diagram a little bit differently, maybe my house was over here, and I would have taken away y. Perfectly fine, as long as you're consistent then. But for our problem, I drew my house along that x side, so I took away an x. All right, so let's go through now and go through the actual process of going through the kind of constrained optimization process. So step 0 was figuring out, getting all the preliminary work done, diagram, variables, and then just figuring out what your equations might be. Now step 1, we're going to actually figure out what is our objective equation, what is our constraint equation. So first, the objective equation is what we want to maximize or minimize. So we're looking for wording that says most or least or something along those lines. And what we're seeing here is we want the largest garden. And so the way we would measure that is with area. So our objective equation is going to be our area formula. And we said that was x times y, area of a rectangle. Now our constraint equation, this puts some restriction on how large our garden can be. So the thing that's putting some limitation on what we can do is the fact that we only have 40 feet of fencing. So we're limited by this. So usually if you see like a constant term in your problem, that's going to involve the constraint equation. So we have 40 feet of fencing to work with. That's going to be our constraint equation. So let's write down our formula for the amount of fencing. And we said that it was x plus 2y, and we know this must be equal to 40. So there are our two equations. Area is our objective, and the amount of fencing set equal to 40 is our constraint. Now in step 2, once we have those two equations, and that's normally the hardest part of these problems, is just getting to that point, getting to those two equations. Once we have them, it's a little bit more kind of, formulaic on how you go through this. So step 2, let's take that constraint equation and let's solve it for one of our variables. Doesn't matter which one. Now you want to make it easy on yourself. So x is a little bit easier. There's no number in front of it. so let's solve for x. And when we do that, we get x is equal to 40 minus 2y. And then we're going to plug that into our objective equation, our objective. So we get area is equal to, instead of x, we're going to plug in that 40 minus 2y. And we're going to end up doing some calculus with this, so let's multiply things out. So we get 40y minus 2y squared. So there is our objective equation with the constraint plugged in. And notice we're down to one variable now, so we can go through all of our usual calculus techniques. And that's what we're going to do next. So we're going to optimize our one variable function, which we said was 40y minus 2y squared. And same process that we've been doing, critical numbers, classify the critical numbers, and then make sure we've answered the question. All right, so let's calculate for our critical numbers. We just want to get our derivative. And then we're going to set our derivative equal to 0 and look for where our derivative is undefined. So usual critical number process. Derivative, set the derivative equal to 0, look for where the derivative is undefined. All right, so let's get a prime, our derivative, and it's 40 minus 4y. That derivative is just a polynomial, so there's no place where that's undefined. So there's no division, no square roots, no logs. So there's no place where our derivative is undefined. So we only need to consider where our derivative is equal to 0. So if we set that equal to 0 and solve for y, we get y is equal to 10. And that's our only critical number. And we know it's a critical number because it's in the domain of our function a. We could plug 10 into that, and there's no division, there's no square roots, there's no logs. So that's in the domain of our function a. So we want to classify it then, and we have some choice, first derivative test or second derivative test. We'll do the second derivative test. Usually it's a little bit quicker, if it works. If it doesn't work, then you would have to use second derivative or first derivative test. But let's calculate our second derivative. It's -4. And we'll write this out in function notation. So a double prime of y, just saying our variable is y, is equal to -4. Then we actually plug in our critical number. And our second derivative here is just a constant function, so it's always -4. And to see what our second derivative test says, well, our second derivative is negative, which means concave down. Drawing the concave down shape, and we see that our second derivative test says we have a local max at y equals 10. Now, we only found one critical number, so it's a little bit more than that. It's the absolute max. So we found an absolute max value at y equals 10. All right, so that just about does it. The last thing we want to do is make sure we answer the question. So what it's asking for ultimately is we want to find the dimensions. So there's two dimensions of a rectangle. We found one of them. We have to figure out the other dimension. So we just want to make sure we're answering the questions here. So we know y is equal to 10. And we want to figure out what x is. And that's where we use our constraint equation. So we're going to use our constraint equation to figure out x. So we know x was equal to 40 minus 2y. So when we plug 10 into that for y, we get x is equal to 40 minus 2 times 10, which is 20. So y is equal to 10, x is equal to 20, but a little bit more. Want to make sure we're using units. So if units are specified, then we want to include those as our answer. So here, the dimensions are in terms of feet. So there's a question. I do want to see if this does happen. I do want to see some sort of mention that, so the question is this arrow, this implication arrow. I do want to see some mention of that on an exam if we're trying to find the absolute max or the absolute min. So second derivative test says we only have a local max. But we're trying to find the largest value of this problem. And so we do want to see that implication saying not only do we have a local max there, but we actually have an absolute max. So just, you don't have to show it exactly like that, but some mention that since we only have one critical number, we can actually say a little bit more. It's not only the local, it's an absolute. So we do want to see that in the classification here, if it's applicable. All right, so we've answered the question, we found the dimensions, and if we go back to our diagram, that seems entirely plausible. So x was 20 and y was 10. So it sort of makes sense that the longer side is going to be opposite the house because we don't have to fence in one of those sides. So that seems entirely plausible. Let's try another example. So we're going to do another rectangular enclosure. So let's read through it. We are going to build a 600 square foot rectangular enclosure on some store's parking lot. And 3 of the sides are going to use redwood fencing at a cost of $14 per linear foot. And then a 4th side is going to use cement blocks, which costs more. They cost $28 per linear foot. So what we're ultimately going to do is we're going to figure out how to make this enclosure as cheap as possible. But before we even get there, we want to just kind of figure out what's going on with this scenario. And sort of that's our step 0. Before we even really get going, we're going to do our diagram. We're going to introduce our variables, and we're going to kind of just think about what are some possible equations that we might want to consider for the setup. So let's start by drawing in our rectangular enclosure. So we're going to be fencing something in. So let's draw our rectangle. And rectangles have 2 dimensions, so x and y. All right, so there's our basic diagram. And what we're going to do is well, 3 sides are going to use redwood fencing. So let's say this side is going to use the wood fencing. This side is going to use the wood fencing. And this side is going to use the wood fencing. So as long as you're consistent, it doesn't matter which one you choose, you'll end up with the same result. You just have to be consistent. And then this other side here, this is going to be our cement wall. And so what are some possible kind of values we might be interested in? Well, area of a rectangle is x times y. We might also be interested in the perimeter. And perimeter is just go through and add up the lengths of the sides. So x plus y plus x plus y. So that might be a possibility. But we're seeing some mention of cost here. So let's investigate what the cost of building this fence would be. And so if we let's start with this wood side on the left. What would be the cost of building fencing along that side? Well, we know wood fencing costs $14 per foot, and we know that the length of that side is y. So it's cost times the length. Then let's look at the bottom side here. That's also wood fencing. So it costs $14 per foot, and x is the number of feet, number of units of length. So the cost for that side is 14 times x. Then for the right side, cost is $14 per foot, and y is the number of feet. So 14 times y is the cost for that right side. And then finally for our cement wall costs, what does it cost? Costs $28 per foot. And the length is x. So the cost for that top side, that cement wall, would be 28 times x. And if we simplify that, just combine like terms, we would end up with 42x plus 28y. So we're not going to use our perimeter equation exactly, but it's sort of similar to what we're seeing in this cost equation, except some of the there's coefficients really that we're doing. There's coefficients of these terms, and that represents the cost of building that side for our fence. So we're not going to use that perimeter formula exactly. We've modified it a little bit so that we're going to be dealing with cost. All right, so now let's actually go to the problem. We have these different gadgets we might be considering for our diagram. Area in terms of x and y, possibly cost, possibly perimeter. But we want to find the dimensions of this enclosure that minimize the total cost of our building materials. So the next step is to identify the objective and constraint equations. So for our objective, that's what we want to maximize or minimize. So you're looking for wording saying largest or smallest or something along those lines. And we want to minimize the total cost. So our objective is going to be cost. And we figured out what that was. It was 42x plus 28y. Now our constraint, that's the other equation we want. This provides some limitation for our variables x and y. So if we look at this, we're limited by the fact that our enclosure needs to be 600 square feet. So that provides the constraint, the limitation. So we're limited by the area. So our constraint equation then, We know the area of a rectangle is x times y, but this needs to be equal to 600. So we've identified the objective equation and the constraint equation. Now we want to go through and sort of reduce this down to a one variable problem. So we're going to solve the constraint. We can do it for either x or y, so whichever one's easier. Here, it doesn't matter. They're both equally as difficult. So let's solve for y because that's kind of what we usually do. So if we solve for y, we get 600 divided by x. Then we're going to take that value and we're going to plug it into our objective function. So that's the next step. We're going to plug that in. And so when we do that, we get c is equal to 42x plus 28. And then instead of y, we're going to write 600 over x. And then if we simplify that down, we know we're going to be doing a derivative eventually, so let's write that with a negative exponent. So 28 times 600 is 16,800, and then instead of having the 1 over x, we'll write that as x to the negative 1. So we've got it to a point where it's a one variable function now, and we can go through our usual optimization. Find the critical numbers, test the critical numbers, and so on. So that's what we're going to do next, is we're going to go through and optimize this. So our cost equation in terms of one variable was 42x plus 16,800 times x to the minus 1. And let's figure out the critical numbers of this function. So we're going to get c prime. So let's do the derivative. Derivative of 42x is just 42. And then we differentiate that other term. We end up with negative 16,800 times x to the negative 2. And we're going to want to figure out where this is 0 and where it's undefined. So let's write this as a fraction, and we'll try to write it as a single fraction. So if we do that, we get 42 minus 16,800 over x squared. Combining those terms by a common denominator, we get 42x squared minus 16,800 all over x squared. So we've written it as a single fraction, and we want to figure out where our derivative is equal to 0, where it's undefined. And when we've written it as a single fraction, that's where our numerator is 0 and where our denominator is 0. Nice thing about getting it as a single fraction is we can just look at the numerator, look at the denominator, and that'll cover all cases. So if we set our numerator equal to 0, 42x squared minus 16,800, and if we solve that, we get x squared is equal to 16,800 over 42, which ends up simplifying to x squared equal to 400. Do the square root of both sides. And whenever we apply the square root, we put a plus minus in front. So this ends up being plus or minus 20. All right, so then we want to figure out where the derivative is undefined. So we take our denominator, which was x squared. We set that equal to 0. And when we solve that, we get x is equal to 0. So right now it looks like we have 3 critical numbers that we need to consider. But we're talking about an actual applied problem here. So we're talking about physical dimensions. So that means length. If we're going to be building a rectangular enclosure, we can't have negative lengths. We really can't even have a length of 0. So that means our lengths need to be greater than 0, which really means our x and y values need to be greater than 0. So when we set up this cost function originally, the domain is really the interval from 0 to infinity. Those are the only x values that we're actually considering, things greater than 0. So we found one critical number then. Well, we go through our critical numbers and we go figure out which one's actually in the domain of our function. And that means we're going to only consider x equal to 20. We're not going to use the negative length, so no negative 20. We're not going to use length 0, so no x equal to 0. The only length we're going to consider here is 20. All right. So we found our critical number on our domain, which is the interval from 0 to infinity. It's only one critical number. Now we need to test it. So that's the next part of this, is we're gonna test it. We're gonna classify it, and normally the second derivative test is a little bit quicker, so that's what we use. So that means we need our second derivative, and if we do our second derivative, that's 33,600 x raised to the minus 3 power. And what we're going to do is we're going to just evaluate our second derivative at our critical number. So we're going to take our critical number, which was 20. We're going to plug it into that second derivative. And we end up with 33,600 times 20 raised to the power negative 3. And for the second derivative test, we don't really care what this value is. We just want to know, is it positive or negative? So 33,600, positive. 20 raised to the power negative 3, positive. So in the end here, our second derivative value is positive. So positive for second derivative means concave up. So to help remember what the second derivative test says, let's draw in our concave up shape. And we see that we have a local min at this critical number. Now, there was only one critical number on our domain, which was the interval from 0 to infinity. So that actually means we have an absolute min at x equals 20. So we found the x value that gives us the minimal cost of building this enclosure. Now we just want to make sure we actually answer the question. And that's the last step. We just want to make sure we go through and find everything that the question is asking for. And so for this one, ultimately what we want to do is we want to find the dimensions. So that's the x and the y value. So we found x was 20. And to get the y value, that's where we go back to our constraint equation and figure out the y value. So y is equal to, what did we have? 600 over x came from our area. We solve for y. Then we plug 20 into that. And we end up with 30. So our y value must be 30. And then we just want to be careful, make sure we're using correct units. And we see that we're measuring things in terms of feet. So our units here are feet. And this seems entirely plausible. So we found our x value was 20, our y value was 30. So let's just go back to our diagram. We found our x value was 20 and our y value was 30, and that makes sense. We would want our cement side to be smaller because it costs more to build that side. But if we make that side too small, then we're going to be building this extra large fence, and things are just going, the cost is going to go further. So there's some sort of balance between how small do we make X versus how kind of large do we make Y. And so we figured out what gave us the minimal value. It was an X value of 20 and a Y value of 30. All right. We're going to try one more example, and we'll save this one for next time. I'm going to jump ahead a little bit, though, and we're just going to talk about some common geometric formulas that kind of show up in a lot of the applied optimization problems that we're going to look at. And first one is one we've looked at in the two examples today, is a rectangle. So a rectangle has two dimensions, x and y. And some of the usual things that we calculate with a rectangle, as we've seen, are area, so x times y, and perimeter. So 2x plus 2y, where we go through and add up all the sides, the lengths of the sides. And then we looked at some other examples that sort of involve perimeter, but we had to make some alterations. So we had to adjust for cost or removing a side or something along those lines. But those are the kind of the two usual starting places for your rectangle equations. Then let's see, might have a box. So maybe we go up to 3 dimensions. We have a rectangular box. So here we have x and y maybe giving us the rectangle on the base, and then we have a height to it now. So maybe a third variable, z. So what are some usual things that we would calculate with a rectangular box? Well, we might want to measure the space inside, and that would be the volume. So that would be x times y times z. So that's one possibility. Another possibility is the surface area. So this is sort of analogous to the perimeter for a rectangle, but now we're just going to add up the area for all of the different sides of our rectangular box. So, and I'm going to do this down here, we might do x times y, which gives us the area of the base. We might do x times y, which gives us the area of the top of our box. And there's 6 sides for a rectangular box. So we've done the base and the top. So what about the right side and the left side? Well, if we look at the right side of this rectangular box is a rectangle with dimensions y and z. So to get the area of that right side, it would be y times z. And same for the left side. So this is for the right and the left. And then for the front and the back, the front side is another rectangle, dimensions x and z. So the area of that rectangle is x times z, and then same for the back. So if we're doing a rectangular box, there's 6 sides. If we're fully boxing this thing in, there's 6 sides. There's the base, there's the top, there's the right, there's the left, there's the front, there's the back. We've got 6 sides. Now in some problems that you'll see, maybe we remove one of the sides. So kind of play the same games that we were doing with perimeter. But if we simplify this, we get 2xy plus 2yz plus 2xz. And then really quick, just 2 more type shapes. Might have a circle with radius r. And so 2 common things that we calculate with a circle are the area, and that's just pi r squared. And then we also do the, well, perimeter, I guess, circumference, we call it specifically for a circle. And that's just 2 pi r. And then maybe we sort of extend the circle to 3 dimensions, and we would get a circular can, cylinder. So circle would have radius r, but now we have a height to it, so height h. And what are some usual things that we calculate with a cylinder? Well, we might be interested in the volume. So that's just the area of the circle times the height, so pi r squared times h. And then we might also be interested in the surface area. So kind of go through, what is the area of the base of the cylinder? What is the area of the top? So the area of the base and the area of the top are the same, just the area of a circle. And then the only thing left that's a little bit different is the area of the sides, which is like, if we were thinking of it like a can, it would be the label of the can, and that would be their circumference times h. So it would be 2 pi r times h. So the surface area for this can would be 2 pi r squared. That gives us the area of both the top and the bottom. And then the 2 pi r times h, that gives us the area of the sides of our can, the side of our can. So those are just some common type formulas and geometric shapes that you might see in some of the homework problems. So just to be aware of. All right, so we'll finish off that last example next time, and then we're actually going to get started in our new unit, which is integration. So this will be sort of, we're moving into the last general topic for the course, which is going to be integration, and we'll spend a bit of time there. All right, so let's stop for today. We'll finish off that last example for optimization next time on Thursday, and we're going to start integration. Just a reminder, we have recitation exam 5 today if you have Tuesday recitation, or on Thursday if you have Thursday recitation. And good luck studying. I also posted, if anyone wants to discuss their midterm grades, if you go to, on our course website, if you go to the progress report for and midterm grade post, there's a link where you can schedule a meeting with me. I have some times for tomorrow, so just, take a look. If any of those times works for you, you can reserve a 10-minute block there. So if you have any concerns about your grade and just want to talk about where you stand in the course, feel free to schedule an appointment and we can kind of look things over. All right. So good luck studying, and we'll see everyone on Thursday. Bye-bye.